Hello and welcome to this tutorial on how to deal with Postgres timestamps and the chrono crate in Rust to fix the precision mismatch between nanoseconds in Rust and microseconds in the database. Alright, so let's see an overview of what we're going to do. So we're going to see how to trim the precision of timestamps in Rust with timestamps coming from the chrono library, and we're going to see why we have 9 decimals and then 6 decimals. Then we're going to open a database connection and eventually we're going to close it. We're going to set up a sample table that is going to store Postgres columns of type timestamp TZ. So the usual timestamp columns in Postgres that have 6 decimals, so microseconds. Eventually we're going to clean the schema just to keep things tidy up. Then we're going to prepare a structure in Rust that represents a row for this table, and we're going to assign to one of the fields of this structure the type of datetime UTC for the chrono library. So this is going to be representing microseconds, 6 decimals, rather than nanoseconds, 9 decimals. Then we're going to insert a row with this data. Then we're going to retrieve this row and store the data coming from the database in another instance of this structure. Then we're going to compare the two structures. And we're going to see also a bit about the serialization of structures in Rust to become JSON strings and how we deal with the representation of timestamps. All right, so let's go ahead and start by importing some modules from the crates we define in our cargo.toml file. So here you see the main dependencies are the chrono crate and the Postgres crate, but we also have a couple of dependencies for the Serde crate that allows us to serialize and deserialize Rust structures into JSON strings. Okay, so let's add these imports. So here you can see that we are importing from the chrono crate some functionality that allows us to represent milliseconds with Serde. Now, originally we're talking about differences between nanoseconds in Rust and microseconds in Postgres. However, from the standard code, we can only render timestamps in milliseconds, but we're going to talk a bit more about this later. We can provide some sort of custom serialization and deserialization functionality. So if we want to implement the one for microseconds, we can in principle. But this is only about JSON strings. So let's go back to the relationship between chrono timestamps in Rust and Postgres timestamps in the database. So here you see we are importing some chrono functionality, some Postgres functionality, and the stuff about the Serde serialization. Okay, so let's start by seeing what we're talking about when we're talking about decimals for timestamps. So here we can see that by invoking the chrono UTC structure and then the function now that returns an instance of type datetime UTC from the chrono library, the timestamp is with 9 decimals, so nanoseconds. However, via this method from the chrono library, we are able to round the precision to, for example, 6 decimals, so microseconds, and that's the precision that the Postgres field of type timestamp TZ is expecting. So here you see we have the Postgres timestamp tz expectation. So we're gonna print these two timestamps and we're gonna see and compare what's the output. So cargo run. Okay. So here we can see that this timestamp coming from the chrono library has 9 decimals. And this timestamp that has been rounded via the chrono library has 6 decimals. So this is a timestamp that is compatible with the Postgres timestamp tz field or type. This is not compatible. So there's going to be some issues arising from this nanoseconds and the timestamp type in Postgres. Okay, so let's open a database connection. So I'm going to copy some code here. And here you see we are connecting to a Postgres server that I'm running on my laptop. The password is this one, this is the user, and this is the name of the database. Now, just to avoid leaking sockets and making sure that everything is clean, we're gonna also directly close the connection at the bottom. Here you see we are already dropping a table if it exists, and we're going to talk about this table in a moment. And also we are closing the database connection. As usual, this is Rust code, so the functionality is returning a result that could be either okay with some data or with an error. So we're making sure that the result is okay, and then when we close the connection that is also returning a result, we're making sure that the result is okay. All right, so let's go ahead and set up this sample table. Okay, so here you can see that we are using the batch execute method applied to the DB client, which is an instance coming from this functionality from the Postgres crate, the dependency we are importing. Well, we're dropping the table if it's there, and then we are creating the table if it's not there. And this is a very simple table. We have the usual ID column that you see in all tables, all databases. And then we have a field of type created on, sorry, a field named created on, and the type is timestamp tz. So, and we know this has a precision of microseconds, so 6 decimals. We make sure the result is okay, so there are no errors. And then we're going to prepare an instance of a structure in Rust that represents a row that we're going to flush into this table. So let's go ahead and define this structure. All right, so here you see that we have defined a structure called TS example. We have a public field called ID of type I32. And then we have a public field called created on that is actually an option coming like the usual pattern in Rust. And the type is datetime UTC. So this is stuff coming from the chrono library. Here you see we are adding some attributes that allow us to compare instances of type TS example together to see, for example, if they represent the same information, and allow us to deserialize and serialize them in, for example, into JSON strings. And this is what we're going to do with the Serde library. Okay, so let's go back to our code and instantiate a new instance of this structure. Okay, so here you can see that the ID is 1 because this is going to be the first row of the table. And because this is an option, the created on field, we invoke the sum functionality from the Rust code base. And then this is chrono code, and you can recognize this round subsets that is gonna round a timestamp with 9 decimals to a timestamp with 6 decimals. Here you have some reference to the official documentation, so go ahead and read about it. Here you can see how they define the type timestamp TZ in Postgres with microseconds, and here you can see how they define the chrono datetime UTC type with 9 decimals, so nanoseconds. All right, so let's go ahead and insert this row in the database. Okay, so here you see some SQL. We are injecting the 2 parameters for the 2 columns of the row, and they come from the structure we defined earlier. Okay, as usual, the execute method returns a result, and we make sure that the result is okay. Now let's retrieve this information from the database and store that information into a new instance of type TS example, so we can compare the original instance with this new instance with the data coming from the database. All right, so here you see the SQL. Because query is returning a result, we unwrap this result, so we get back the OK value for this row, and this is actually a vector containing data of type Postgres row. So this is coming from the Postgres dependency. This is the standard library for a vector. We know this is going to be only one row, so we just initialize an instance of type TS example with ID -1, and because this is an option, we're going to use sum and then UTC now. This is coming from the chrono functionality, but just after doing this, we're going to iterate through this vector, and for each row, and we know there's only one row, we're going to get the data coming from the database. So this is going to be the ID 1, and this is going to be the created on data from the database that hopefully is going to represent this same information when we inserted this into the database before. Okay, so let's go ahead and run this to see what's the output. Oh no, 1 second. First we need to actually print and compare this information. So here you see the structure that we inserted into the database, and here you see the structure that comes from the retrieval of the information from the database. We make sure they represent the same information. Let's run this and see if it's true. Yeah, my laptop takes a while because it's not the latest version. All right, so here you can see that we represent the same information with the expected number of decimals, so 6 decimals. So this works both with the database types timestamp TZ and the chrono datetime UTC types for Rust that are originally with 9 decimals, but actually we downgraded them to 6 decimals. Okay, as a last thing, we're gonna see the JSON string serialization, and we're gonna talk a bit about epochs. So let me copy some code. Okay, so as a standard functionality from the chrono and ser dependencies, we can serialize into string our structures, our instances, so the one that we use to insert data and the one that we use to represent the data coming from the database. And because in the definition of our structure we are using this functionality from the CERD library. This is standard functionality and is representing epochs only in milliseconds. So we're gonna see basically, sorry, let me pick, yeah. In our JSON strings, we're gonna see basically milliseconds as numbers that represent epochs. However, we know we can provide our own implementation for the serialization and deserialization of timestamps. And for example, rather than using the millisecond standard implementation, we could provide an implementation for microseconds epochs, or even a representation with strings with the usual format we are used to. Okay, let's go ahead and run this to see what's the output. Okay, here you can see that the JSON representation of the structures has epochs. You can use this website to check the epochs in human readable form. We know they represent milliseconds when serialized. We know how to provide custom serialization and deserialization functionality to, for example, represent microseconds or strings in the usual format. So that's it for today. I hope you enjoyed this journey in checking differences between Rust timestamps and database timestamps. Happy Rust coding to everyone, and I will catch you on the next one.